Hello everybody and welcome again in your channel Thermal Engineering Concept and Principle. In previous episodes we talked about how to predict the heat transfer coefficient for fluids while they pass through a tube in a laminar and turbulent flow. In the present episode we will go through how can we estimate the heat transfer coefficient of fluids as they pass over the outer surface of the tubes. That is called the external flow. Let us go deeply in our episode, which is presented by Professor Ali Talat. Dear colleagues and friends, and welcome again. Uh, we passed through the estimation of heat transfer coefficient for fluids that pass over a single tube, and we introduced some correlations to predict the heat transfer coefficient in such cases. In the present episode, we will continue to talk about convection heat transfer coefficient for external flow for the case where we have smooth tube bank. Of course, most of the applications in the industry where these banks are used in a form of heat exchangers, and most of them in what we call is the air-cooled heat exchangers, and usually they are composed of finned tubes, but some applications include a straight smooth tubes as well. So in this part, we will give some useful correlations where we can use them to predict the heat transfer coefficient of fluids such as air passes over tube bank. Thank you for your support, and let us go to the objectives of the present video. The objectives of the present episode cover external flow over tube bank concept, and we will describe that in industrial application of heat exchangers. Available correlations in the open literature, we will mention some of them and examine them in a practical case study where air flows on these tubes. And finally, we will arrive to the closure of the present episode, and let us go through these objectives. External flow over a tube bank has numerous industrial applications where they are needed in different uh, fields and topics such as power plants, refineries, or petrochemical sites, food factories, and many other applications. Such application is shown in this figure where heat exchangers are used to cool down the lubrication oil of a gas turbine engine. And in this application, we have air-cooled heat exchangers. Although they are finned tubes, but it is uh, representing one of the applications where we can use the external flow over a tube bank. Here, the red arrow describe the hot side where the oil is withdrawn from a tank, passed through two heat exchangers, and then the cold uh, side is presented by the blue line, where it is leaving the heat exchangers and return back to the to do the lubrication uh, objectives. This is a simple diagram for such application, and we will go through many others in the near future by many correlations and applications where can be presented. Types of tube arrangements. Usually they are presented in a category called inline bank, where all the tubes are having at the same center line as shown in this figure, and a section can be taken to estimate the flow area, which represents the minimum flow area for inline bank, as shown in this diagram. We have XT and XL. XL represents the longitudinal center to center distance, and X sub T refers to the transverse distance, as shown in this figure, which is perpendicular to the flow of the fluid. Uh, the following relation uh, gives the maximum stream velocity, which passes through the minimum area. U max equal U infinity times xt divided by xt minus d naught, as represented by equation number 1. And we have another arrangement called the staggered, as shown in this diagram, where the minimum area is referred to as A substagnant, staggered, and it is calculated in the terms of uh, xt and xl together with d naught, as shown in equation 2a, and then u max is represented by equation 2b. In fact, we need these parameters when we want to predict the heat transfer coefficient for fluids as they pass through uh, the external side of tube bank. Some of the available correlations are presented here. One of the famous of these correlations is prepared by Grimison in 1937, and it is represented in the form that Nusselt number equal to constant Reynolds maximum to power m, and the Prandtl of the fluid to power 1/3 for Prandtl uh, of the fluid greater than zero point 0.7. He listed the constant C and M in tabulated form, table 1, and the property should be calculated at the film temperature. Here we have uh, the main parameters xl divided by d naught and x sub t divided by d naught. And here we have a range of these values which can produce different values for C and M as shown in this table. These values depend on, of course, the form of or the arrangement of the uh, tubes, uh, inline and staggered. From these values, we can get um, these the factors, the exponent m and the constant c. For example, if we have xl divided by d naught equal 2 and x sub t divided by d naught equal 2, then we will get values for c as 0.254 and m 0.632, and similarly for other different values of these ratios. Of course, we have to point out that these constants are obtained for two banks, 10 rows composes of 10 rows or more. For other number of rows less than 10, for example, 5, and we have n equal 1, 2, 3, up to 10, then the value of heat transfer coefficient as obtained from equation number 3 should be multiplied by these factors. For example, if it was uh, line cube with the n equal to 4, then the factor should be 0.9, and for staggered, then we will get 0.89. These correlations are based on Reynolds uh, number, maximum velocity or maximum Reynolds number, and usually it occurs when we have minimum flow area. That's why we calculated the flow area before we arrived to this correlation. The COSCAS has also published one of these correlations in a similar form to that of Grimison one. Again, Nusselt number is constant times Reynolds maximum to power m, Prandtl to power 0.36, with a parameter to include the effect of wall temperature on the thermal physical properties of the fluid represented by Prandtl number. This is this equation to be used under some restrictions. The first is related to Reynolds maximum greater than 10 and less than 10 to power 6, and the Prandtl number is greater than 0.7 and less than 500. The coefficients C and M were also obtained for a tube bank that is composed of uh, 20 rows or more, as shown in table 3, where the values of C and M are presented and listed in this table for the inline and the staggered tube arrangement. Of course, to get the heat transfer coefficient for uh, bank, tube bank, where the tube number, the row numbers less than 20, he has also presented a table as shown in table 4, where the correction factor should be applied to equation 4. And again, Reynolds number is based on the maximum velocity which is occurred in the when the flow is obtained for the minimum flow rate. As shown in table 4, let us consider the number of rows are 8. Then for staggered tubes, we have a factor 0.97 to be multiplied by the value obtained from equation 4 with the help of table 3. And then if it is in line with 4 row numbers, then we will use 0.9 to be multiplied by the results obtained from equation number 4 as well. Practical case study. Let us consider air at 1 atmosphere and 15 degrees centigrade passes over a thin tube bank at a velocity of 6 meters per second, measured at the free stream in a cross section and a cross flow. That is shown in figure 1. The bank are arranged in the tubes of this bank are arranged in a line as shown in the figure, and it is composed of 8 rows and 4 rows in the deep and 8 rows high. The diameter of the tube is 3/4 inch with longitudinal and transverse direction xt and xl and xt as a value of 1.125 inch. We have to determine the heat transfer coefficient of airflow where the wall temperature of these tubes are kept at 50 degrees Celsius. The solution is related to obtain the properties of air film temperature, and film temperature equal to T infinity represent the bulk temperature of air plus TO divided by 2. Then we will get 35 degrees centigrade with the help of air physical properties tables. We will get raw density, specific heat, thermal conductivity, dynamic viscosity, and a Prandtl number measured at film temperature. Also, we need the Prandtl number to be obtained at wall temperature, which is equal to 0.7215. Then we may calculate the Reynolds number maximum rho sub f u max d naught divided by mu f, and u max is obtained from the equation which we have already listed in this video. Then Reynolds number will be 20,718.8. With these values, then we will try to use the published correlations or the mentioned correlations in this video. Let us first try Grimson correlation, and to start we have to calculate the dimensionless parameters xt divided by d naught and xl by D naught, which were equal to 1.5. With table 1, then we will get C 0.278 and M equal 0.62. Of course, equation 3 as presented, this expression can be used to get the Nusselt number equal 118.58, and with the definition of Nusselt number, we may get the heat transfer coefficient of air to be 163.4 watt per meter Kelvin. And because the tube bank has only 4 rows in the flow direction, then table 2 may be used to get the correction factor equal 0.9. And finally, the heat transfer coefficient is equal to 147.1 watt per meter square Kelvin. This is by Grimson correlation. And the Kuskas correlation may be used as well with equation number 4 as presented in this form, and with the knowledge of all these parameters, of course, from table 3 can get C equal 0.27 and M equal 0.63. The Nusselt number, if we substitute these values in equation number 4, we will get Nusselt number 126.93, and with the aid of Nusselt number definition, we may get heat transfer coefficient equal 165 watt per meter square Kelvin, and we need to use a correction factor from table 4 because the number of rows in flow direction were less than 20. Then the coefficient correction factor 0.9, which is obtained from table 4, should be multiplied by 165 to get the final heat transfer coefficient of air as it passes through this tube bundle equal 148.5 watt per meter square Kelvin. Dear friends and followers, we have arrived to the final section of the present episode. That is the closure. We covered external flow concept and industrial applications, and we have mentioned that it is mostly used in the air-cooled heat exchangers, where a Fendi tube type can be used, or it must be used, in fact. Then the prediction of heat transfer coefficient for flow over tube bank was mentioned, and 2 of them are presented. And if you want to know more, please visit the references which are listed in this episode. Then we went to practical industrial case where we can describe and how to use the correlations as given in a case study. And if you feel that this information is useful to you and others, please subscribe and share the information. And I will see you in the near future. Bye-bye.